All right. Hi, guys. Chemistry class, and this
Hi,
is
guys.
Unit 1 and 2. Mrs. Goswish, and this is Mr.
Hi, Mr. King.
Mr. King.
All right, here we go. We're going to talk about the things that really matter today. I had to get that in there.
All right. Unit goals. You are going to be able to identify elements, compounds, pure substances, mixtures, homogeneous solutions, heterogeneous solutions.
All right. If you can identify all those things, you're going to be able to distinguish between chemical and physical changes as well as chemical and physical properties. All right, start out with matter here. Good definition of matter is anything that has mass and takes up space. If you start really thinking about it, the macroscopic scale, the sun is one of the largest things in our solar system, and it has a lot of mass and it takes up a lot of space. It's made of matter. That nice little car there, Mrs. Goswish.
My favorite car.
Okay, if anybody wants an A, we know how to get
Mini
an
Cooper
A.
convertible. There you go.
Red. It has to be red.
Yeah, it has to be red.
All right, but at any rate, a mini convertible has mass and it takes up space. Matter of fact, the air inside of that Mini Cooper has
Awesome.
mass
That
and
is
takes
correct.
up space.
The air you're sitting in right now has mass and takes up space.
Hate to drop the balloon on you, but air does have mass. And then that last cell there is a picture of cells fluorescing under a microscope. So even cells have mass and they take up space. So all matter is composed of atoms. All right. These are the smallest building blocks of matter that we know of and talk about as we talk about chemistry here. And it turns out that one of the ancient Greeks, Democritus, first describes the word atomos. Because he believed way back in the time of Plato and
Me.
Mrs. Goswish. You can look that up, but Democritus was thousands of years ago. I think it was nearly 2,000 years ago when he
Yeah.
came up with this word atomos to describe the smallest bit that matter could be divided into. That's what he believed that matter was
Didn't
made
they think that everything was made of like fire, water, and something else?
of. Yeah, fire, earth, air, fire, and water.
Yeah.
Or is that a band?
It's a band too.
All right. Here's the basic idea that we know of today. So you go from Democritus over 2,000 years ago to today. We've got what are called scanning tunneling microscopes. A scanning tunneling microscope doesn't use light like a light microscope does. It actually has to use something that's even smaller than light. It uses electrons. So it fires electrons at these little targets that they make up. And since we can't actually see electrons, a computer detector has to detect the electrons bouncing off of the object that they put in the microscope, and has to make up a picture of how many electrons are hitting and where on the detector. So the white sections on this picture that we have represent high densities of electron clouds, and the darker areas are representing low densities of electron clouds. It's kind of like an X. The little white dots that you're perceiving are electron clouds of graphite, which is carbon. So what you're seeing is lots of little carbon atoms kind of lined up here. Pen.
So graphite, isn't that what a pencil is?
Yep. Graphite is what pencil. You see, there's a carbon atom. There's a carbon atom. There's a carbon atom. There's a carbon atom, and you can see that this is almost made something of a crystalline structure of carbon.
Atoms and elements. Every element on the periodic table is made up of a single type of atom. So a couple of examples there. The one on the left is elemental carbon, and it's only made up of one type of atom, a carbon atom. And carbon, the picture on the top shows carbon with its 6 protons, 6 electrons, and the 6 neutrons in the center.
Mm-hmm.
The picture on the right is also an element, and it's called a diatomic element, di meaning 2, because that is elemental nitrogen gas.
There's one and there's two.
And even though it's an element, and even though there's 2 of them bonded together, they're the same type of atom, and it's a diatomic.
Compounds. Compounds are 2 or more different elements that wind up getting bonded together. Our typical example here is the water molecule. You can see here we've got 2 hydrogens here. Here's a hydrogen here. I'm going to go ahead and circle them here. We've got 2 hydrogens there, and then we've also got our oxygen here. It almost wants me. I almost think of Mickey Mouse when I see this
I was
one.
just thinking the same thing. Those are Mickey Mouse ears.
Yeah. It turns out all water molecules have the same composition, so every single water molecule is going to kind of remind you of Mickey Mouse.
And every single water molecule is going to have 2 hydrogens and an oxygen.
What is that? Constant composition?
Yeah.
There's actually a law about that in chemistry. You'll read it in your textbook. Law of constant composition. All water molecules have the exact same composition. 2 hydrogens, 1 oxygen.
Same ratio, 2 to 1.
H2O. Different states of matter have different properties, and it's kind of interesting to see this. The solids have particles arranged in a regular repeating pattern. You can kind of think back on that. The STM of carbon was pretty regularly repeating. You can see here that the particles actually vibrate just ever so slightly. So it's actually pretty difficult to use an STM because one of the requirements of an STM is that you have to cool off the substance that you're dealing with so that you minimize these vibrations.
Cooling it off would make it slow down, right?
Correct. The slower that the molecules are vibrating back and forth, the cooler it is. They actually stick stuff in liquid nitrogen before they put it in the STM.
Does that mean even the desk that I'm sitting on is vibrating slightly? Because it's a solid.
That's mostly because my leg keeps shaking.
Oh, okay.
But yeah, even the desk that we're all sitting in, they are shaking and vibrating.
So all solids actually have motion. Oh,
Yep.
That's interesting.
And funny enough, the motion is so small that all solids still have a definite volume and a definite shape. So they never actually really change their shape. In general, when you're talking about this, solids have the least amount of energy. You alluded to the temperature and how fast they were moving. It turns out that they're related. They're a measure of energy. Okay, so since they're moving only a small amount, it's a small amount of energy. Liquids, the particles tend to flow easily around each other. As you can see in the little diagram there, those particles are having a pretty easy time flowing around each other.
Is that why you can pour a liquid, but you can't pour a solid?
That's exactly it.
Oh, it flows.
So my question based on that, though, is what is silly putty? Is it a liquid? Is it a solid? Is it both?
Does silly putty flow?
If you let it sit long enough.
Then it must have something of a change of state slightly. Or smack in the middle of the two, which would be strange.
Or maybe I kind of like to think of the world as not being solids or liquids, but it's kind of a shades of gray in between.
Yeah, because don't we make goop sometimes too?
Ooh,
that we can.
yeah, slime.
Yeah,
Halloween.
slime.
That'd be fun. All right, so basic idea here is liquids. Those particles are still attracted to each other. Notice none of them actually start flying up or out of that container that they're in, that orange box. So they all kind of stay towards the bottom with gravity, and they're all sticking towards each other. We definitely have a definite volume. They're not moving all over the place in that container, but they don't have a definite shape. We can pour them out and pour them into whatever size container we want, whatever shape container we want.
You can pour them from you could pour orange juice from a regular old glass into one of those little elephant containers, and it'll take the shape of the elephant.
Yep, there we go. Assuming the shape of all the containers.
Yep.
All right. And the last thing that's really important to talk about here, they've got more energy. Liquids are going to have more energy than the same substance as a solid. Okay, so let's see, water. Water is a liquid. It has quite a bit of energy. If I make it a solid, it's got less energy. Okay, we don't want to compare different things. We don't want to compare like water and a desktop, because that's not fair. We've got to compare the same thing if we want to compare energy.
If it's the same substance and it's a liquid, how would you get that same substance to be a solid?
You steal some energy.
And how'd you do that?
Cool it down. Take away temperature.
Freeze it, put it in the freezer. Oh.
So there's this relationship between energy and temperature.
Gases. Gases do not have a definite volume or shape. Particles are weakly attracted to each other and move at really high speeds.
Yeah, those are even faster than the last one.
Yeah, those are going fast. And gases actually will take up any volume you throw them in. That's why there's no definite volume or shape. You could put oxygen in a small little container, or you could release it to the room and they'll just spread out.
So if I put these in a bigger orange box, what would happen?
They'd spread out. They'd just take up more space. They'd fill the box.
So more space in between them.
More space in between, and you could put them in a smaller one and there'd be less space in between. They're compressible.
Oh, okay.
And if you notice, they're moving a lot faster than the solid or the liquid. So that must mean they have more energy than the solid and the liquid.
Plasmas are the fourth state of matter. Believe it or not, there's actually four. And the funny part is we call it the fourth state of matter, but it's really the first state of matter, because when the Big Bang happened,
Gases.
the entire universe wasn't made of gases. It was made of plasmas. It was extremely hot. All that plasma is, it's a gas supercharged. So there's still no definite volume or no definite shape. And the big deal here is that these atoms have so much energy, they're flying so fast that when they collide with each other, they start breaking each other into pieces. So you can see here in the picture, we've got negative electrons and positive nuclei that have actually been broken apart from atoms.
Oh, they're breaking up.
So that's what a plasma actually is. It's got the most energy of any of the phases of matter that we're aware of. Hey, you know what? Should we offer extra credit right here?
Sure.
There's a fifth state of matter. Be the first person to give either one of us a write-up, a short write-up along with a reference on what the fifth state of matter is, and we'll give you some extra credit. Plasmas are really, really hot stuff, and they're absolutely everywhere. Fluorescent light bulbs have plasmas in them. Lightning, plasma. The aurora borealis, plasma. The corona of the sun, the part that actually is doing the glowing, plasma.
Right. Physical versus chemical properties. Physical properties deals with properties that, when observed, do not change the chemical makeup of the substance.
That's pretty straightforward.
Yeah, ice, liquid water, steam, that's all H2O.
Okay, so physical property might be that ice is cold.
Ice is cold or ice melts. A physical property would be the substance melting. And when the substance melting, it just changes its state of matter. It doesn't
Just
change
changes the
its
state,
identity.
yeah. Okay. Chemical properties?
Deals with properties that, when they are observed, they will have a different chemical makeup of the substance.
When I heat wood up, it burns.
And it becomes carbon dioxide and water.
Okay. It changes. It
Yeah.
changes what it is. It's not
It's
wood
no
anymore.
longer wood.
Right.
And the same with fuel. Fuel is nothing more than a hydrocarbon, but when you light that up, it becomes CO2 and water. No more hydrocarbon. Just burns up.
A physical change is a change where the substance doesn't change its identity or its chemical makeup. So it's got to be the same thing. Usually we're looking for things like a change in states. We're crushing or we're breaking things, or you might be cutting or ripping things.
Melting and heating up too.
Yeah.
I mean, those are two words to look for when you're trying to determine if it's a chemical or physical change. Physical changes are usually just states of matter change, you know. Chemical changes. Chemical changes are changes where the substance will change its actual chemical makeup.
Okay.
Usually, energy is involved. Atoms are not destroyed, just rearranged to make a different chemical substance. Words to look for when you're trying to decide if it's a chemical change: combusts, burns, decomposes into, makes or synthesizes, reacted with, produces, stuff like that.
So words that are saying that it's changing.
Correct.
Yeah. And we got chemical reactions here. The basic idea of chemistry is that you write reactants on the left side, you write products on the right, and you got an arrow in between to indicate that these things are changing into these things.
Yeah, I mean, think about it logically. Flour and water and some sugar, and you basically get pancakes.
Ooh, flour plus H2O plus water plus sugar
Gives you pancakes.
gives you pancakes.
The stuff on the left is different than the stuff on the right.
Yep, definitely different. But it was made from the same atoms.
Yep.
Ooh, and there was...
Energy over the arrow, heating.
Oh, there's energy involved, so we draw an arrow. Yeah, we draw a
Triangle?
triangle above the arrow. Sorry, I couldn't remember that. That's a triangle there, guys. Let me show you. This is how it's actually supposed to be drawn, like that.
So when you heat up the flour, water, sugar, you get your cooked pancakes.
Because you have to cook it. This basically means that we're adding energy. Signs of a chemical reaction. So things you're looking for a chemical reaction that are actually going to tell you the chemical reaction happened. You're looking for a color change that wasn't expected. Gas production. You're looking for lots of energy being either used or produced, and you might be finding a precipitate forming. Precipitates are when I take two chemicals that are absolutely clear, like this, and I add them together, so I pour them into one big beaker. And what a precipitate's going to look like is it's going to look like it's gotten cloudy all of a sudden. Sometimes that's a color change. Sometimes it's not, but we're going to have all this cloudy stuff inside of it. And that's a chemical word, precipitate. That's part of your definitions. Let's talk about these real quick. What happens when ice cream melts? Is that chemical or physical?
Let's see. When ice cream melts, it's still ice cream. It's just yucky ice cream now, so I'm going to go with physical on that one.
Physical? Okay, that's physical. Cars rusting. I know a lot about that one.
Yes, I remember that car. Cars rusting. That means that the metal is changing to a different type of metal.
Yeah,
so
I think the iron is turning into, well, we
iron
call it
oxide,
rust, right?
Yeah, but it's iron oxide, so I'm going to go with chemical change on that one.
All right, iron oxide. Let me catch up here, and that's a chemical change?
Yeah, I'll
All
go
right.
with chemical.
Water boiling and turning into steam.
It's still H2O, so physical, yeah.
But it's water before and steam after. That's different, isn't it?
Not chemically, not the chemical makeup of it.
Ah, okay, so it's just H2O before and H2O after?
It's just a different state of matter.
Physical change then. All right.
Yep.
Milk curdling into cheese, my favorite chemical reaction.
Yep, that's definitely chemical.
Dew forming on the grass.
Isn't it just wet grass?
Yeah, it's
Still
just wet
grass.
Where did the wet come from?
I would imagine it's from the moisture in the air, like overnight or something like that. Settles
Ooh,
down.
When it gets cold, the moisture in the air actually condenses.
Yep.
Okay.
Oh, condenses, goes from gas to liquid.
Yeah,
Oh my goodness,
that's
chemistry.
That's a phase change. That's physical.
Yeah, that's a
All right.
physical change.
People grow older. I don't do that.
I am. I'm going with chemical on that one.
That's chemical. All right. Cement drying.
That's gonna be let's see, if it's wet and goes to dry, it's losing water, right?
Yeah.
So
It's also heating up. Have you ever touched cement that's
I did once,
it's
but I got
curing?
stuck.
Oh, okay. How'd you get out?
Somebody came along and cut my hand off.
Ooh, hey.
It's okay.
All right.
That's a chemical change then, because you are still losing water. So instead of being a hydrate, you're now a dehydrate.
Right. And heat is coming off of that one. You're
Yeah.
actually heating up. The people who put together the Hoover Dam know about that
So
one.
it's losing energy. That's interesting.
In wood burning, the wood's losing energy there. It's giving lots of energy off.
Yeah, and it looks different after it's all burnt. It looks slightly charcoaled, and you get that CO2 and water again.
So we got that chemical.
Yeah, that's going to be a chemical reaction too.
Okay.